Thank you, Chair. Well, first I'd like to thank the organizer, Ionut and Luminita, for put everything together. This is a truly interdisciplinary summer school or conference. It's really physicists, mathematicians, and also computer scientists, everything together. I really enjoy it. Well, just last minute, I decided to change a little bit of my talk. Just little different with the title I gave before. The two reasons: one is I have a new laptop. Seems this laptop has some little problem to show movies, so this talk have less movie. The other is this is the second to the last day of the conference. So now there's many talks on so-called vortices, GP. So I decided to little more mathematical part of my talk. Okay, so this joint work with a lot of collaborators, including Nova Abdullah from Toulouse, University Paul Sabatier, and Yung Cai, who is here, from the Beijing Normal, Leslie Grung at NYU, Shi Dongjiang, NJIT, and Zhen Lei Fudan, and even Han Pu from Rice Physicist. And also Matthias Rusinas, he's graduate from Oxford Physics, doing postdoc with me, and a few other collaborators from China. Okay, a brief outline. I'll begin with the motivation, the so-called dipolar Bose, I consider dipolar quantum gas. And it's mathematical models, basically the GP equation with a non-local interaction, non-local anisotropic, and highly singular. So talk about the ground state, and exists some theory, exists uniqueness, and how to compute dynamics. And also here, people know in experiments, the trapping potential always could be anisotropic. Either so-called the trapping frequency in one direction is much the different scaling separation. So how to reduce the model from 3-dimension to 2-dimension or even 1-dimension. So people said, oh, originally it's an n-body problem. It's a 3n plus 1-dimensional linear Schrödinger equation. Well, n large is very highly challenging. Then use the mean field to get a 3-dimensional model. I was told that for physicists, 3-dimension even also high dimension too. But if someone has kind of a 1D model or 2D model, much easier. So here you will see some 1D model, 2D model. You will get so-called fractional PDE from the reduction, and some rotating dipolar BEC, so some vortices. So we know that there are typical digital quantum gas, including liquid helium 3 and 4. You see a lot in this conference, and also both and condensate of BEC in short, including bosons or fermions, one component, two component or spinel system, or even Bose-Fermi mixture. So these quantum gas, they share some properties, like they have a low microkelvin or ultra-cold nanokelvin temperature. They are realized experiment and the so-called quantum phase transition. And they are closely related to nonlinear wave. So they are called superfluids. That means this kind of flow, they flow without friction. And a typical signature phenomena experiment is they support the quantized vortices. Okay, this like density plot, you have little holes. Okay, and of course the interaction can be contact or local, like a Fermi or local interaction, or Coulomb, even dipole. So the Coulomb, of course, is non-local but isotropic. So later you will see some. Okay, well, so this dipolar quantum gas is kind of interaction is so-called anisotropic and a non-local interaction. So setup is following: you have a molecule, and you have molecule, you several molecule and external like electric field or magnetic field. They form two molecule form a dipole. Dipole like a polymer. They have a direction. So you cool down this dipole to ultra cold and hold in a magnetic trap or a confinement trap. You get a sort of dipolar condensate or degenerate condensate. So this first experiment was realized in so-called 2005 by Cronium 52 and Stuttgart. So this is typical experiment, some first experiment result there. So due to this kind of anisotropic and non-local interaction, the general you have a new freedom to play with this dipole orientation. So the general lot of theoretical study and even experiment study. I heard recently people use this dipolar to study super solids, something like that. So later they I think this is maybe another experiment group using the DY164. They can generate a stronger dipole-dipole interaction, or DDI in short, and they tested this. So this is a profile of the spin gas in different time, or something that shows this is really some kind of dipolar condensate. Okay, this is offspring. So the method model for this kind of problem is so-called the gross-Place equation with a non-local dipole-dipole interaction. So here, t is time, x is spatial coordinate, r3. Psi is a complex wave function. So this psi, after proper dimensionalization, follow this kind of so-called gross-Place equation with a non-local dipole-dipole interaction. So here, so the first three term is a classical so-called gross-Place equation. This V is the trapping potential, beta is the contact interaction, and the last term, this star is convolution. Okay, so you can say V is like a classical harmonic trapping potential, and beta is equal 4 pi n as over a0. As is scalar length. A0 is the non-dimensional spatial unit. And we have a parameter lambda is equal m, the mass of the dipole, n number of dipole in the system, and h bar a0. So, and the mu0 is the dipole constant for vacuum, and the mu dipole for the dipole. Of course, you can say in experiment, this lambda can always bigger than 0, because all this mu is positive. Of course, mathematically you can study lambda some kind of real number. And here, this is star is a convolution. So this kernel U dipole, so the long range dipole interaction is like defined following. So this is like a dipole 1, dipole 2. They have all the dipole aligned with same direction, say n, which is a unit vector in R3 or n in S2, like a 0, 0, 1 or 1, 0, 0. This is fixed. So this is one dipole, another dipole, and this is dipole orientation, this one. And we define so-called, this is the vector between these two dipole, and the angle between the dipole direction and this one. This is called theta. So this is U dipole of x for any position x, defined as 3 over 4 pi, 1 minus 3 n dot x minus over x cube, x square, and over x cube. So this is, or in other words, can written as 1 minus 3 cosine theta square over x cube. This theta is this one. So this is my x vector, this is my n vector. N is a dipole orientation. X is 2 dipole, this one. So you can see here, you literally will see this 1 and 3 is very essential, so that this convolution is well defined mathematically. Because here you can see this kernel, this one, when x go to 0, close to 0, this is basically big O 1 over epsilon x cube, which is if this is not 1, 3, this normally is not integrable. But with this coefficients, one can show that this U dipole of x, this function, any surface in R3, single origin, the integral is 0. Okay. So of course, suppose psi is of this problem, then there's mass conservation. So this absolute size square over R3 is, say, normalized 1, because since I put my n number of dipole into this constant here. So my mass is always 1 from quantum physics. So that you know, this epsilon of x, so this guy defined as rho, which is density or probability density. And another is this kind of energy conservation, this kinetic potential energy. This is contact interaction energy, and this is dipole-dipole interaction energy. You can see this term, since U dipole changes sign. So this term is not, you cannot see whether it's repulsive or attractive, because if you fix the sign of lambda, this one will be, for some part of X is change sign. So here you can see the long range interkernel. It is highly singular, as I mentioned before. It's at when X near origin is as this one. This is highly singular than Coulomb. Coulomb is 1 over epsilon of X. Okay, and so this guy, the dipole, this guy is a Fourier transform. U dipole hat C equal -1. So this you will see from a different formulation. It's very easy to see. 3n dot C square over C square. C is a Fourier symbol. You can see from this formulation here, when C goes to 0, this is 0 over 0 type, but no limit, because here's when C per to n, right? It's and also if create orthogonal to n, this either is 1, is another is 0. So this is no limit. Also, when C go to infinite, also no limit. So, well, based on this convolution formulation, well, so-called we need to compute ground state of dynamics, the truncated bounded domain for convolution. Natural way to do simulation is using Fourier transform. Then when you do Fourier transform, we need to compute it to U dipole hat C equals 0, 0 modes. Just take -1. You drop this term. Then you find that's the numerical locking phenomena. That means when you have a fixed domain, no matter your mesh size, how small it is, the numerical arrow is at 10 to the power -2 or -3, cannot go down. You will see there are some truncation arrow or mismatch of the boundary condition. Okay, so here we see using, if we do another formulation, everything becomes very, also the formulation looks very complicated, but you can see very clean now. So let R equal epsilon of X, like the radius in sphere coordinate. dn equal n dot gradient. N is unit vector. So you can see this is kind of a directional derivative. And dnn equals this one. Then luckily, the physicists are very clever. They give this kind of U dipole equals this one can be decomposed to two terms. Minus Dirac of X. This is a Dirac delta function. -3 dnn 1 over 4 pi r. So this you can see when X non-zero, you can check very easily. When X go to 0, you can integrate this side and you take the singular. That's here is this one. Okay. From this formulation, you can see the Fourier transform is very easy to say. You can say the Fourier of this one, of course, equal Fourier of this one. This one, no, the function Fourier is 1. So this one, you can say, take a Fourier transform for this one derivative is n dot c, right? So dnn, you got this term. And this guy, 1 over 4 pi r in R3, which is nothing but the minus Laplacian fundamental solution. So minus Laplacian is Fourier transform is 1 over is this guy. So it's inverse. So you get this one. So you can say from this formulation, you can get this. It's Fourier transform straightforward. But of course, if you're using before using this one to do using sphere coordinate to do calculate the Fourier transform, it's very, very tedious. You will see several pages to get the result. Okay, after you apply this decomposition, you can get this dipole interaction. In fact, can be further decoupled into two terms. So U dipole comes this one equal minus. So this Dirac comes to this one. A is this one. -3 dnn phi. Phi is equal this one convolution. So this one in R3 is nothing but minus Laplacian phi equal Cette square. So this is a Poisson equation. So if you now plug this guy back into this equation, you can see you have a nice PD formulation without convolution. You get so-called Gross-Pétersky Poisson type, not a Poisson. Because if you remove this guy, it's the standard GP Poisson equation. But here is this one. So you have these two terms are the same. So this term is from the original contact interaction and from part of the dipole convolution, dipole term, and with this term. And the Poisson equation for this one, and of this little phi must go to 0 at far field. Okay? Then the energy functional can be rewrite into kinetic interaction, or potential, and this guy from this term, and this guy from this term. Okay, so you can see my decomposition, principal decomposition, right? You can think as local, non-local. From the energy, this one here, you can see this decomposition can be also regarded as so-called repulsive, attractive. You can see it now with this formulation. If my lambda bigger than 0, so you can see here minus lambda, this guy is attractive. If lambda bigger than 0, this guy is repulsive. If lambda less than 0, this guy is attractive. Then minus lambda times this guy, because beta term is the original term, right? So this minus beta lambda, this one is repulsive. So you can see basically this decomposition can be regarded as local, non-local, or repulsive, attractive. So now you can see with this formula, you can see in terms of energy, these two terms both have clear, it's a clear signal, a sign. Okay. So now the ground state is so-called the ground state is, of course, what you do need to do is from this model here, you take a psi equal exponential minus I mu t times phi of x. So stationary state, not a stationary. Then you plug in, you end up with the following so-called eigenvalue problem. So, all the other definition is, so the ground state is minimize the energy functional, which is given here. This energy functional, and the constraint that, so because here what we study is, because you're given the number of particle, find the minimizer of the energy functional, which is different with chemical potential or different with eigenvalue. So of course, find the minimizer energy functional E of phi for all phi in this set S. S is this phi is as this L2 norm, the mass equal 1, energy bounded. Okay, we see phi G is a minimizer. Okay, of course, from this minimization problem, of course, since set S is unit sphere, even dimension, is non-convex set. So this is a kind of a non-convex minimization problem. Okay, and of course, if we from this minimization problem, it's constraint minimization problem, if we define Lagrangian L phi mu equal E of phi minus mu times this absolute phase square minus 1. You end up with the following square, either call it a nonlinear eigenvalue problem and the constraint, or so-called Lagrangian equation. So here, this problem is we find the mu and the phi together, and of course, and the constraint the phi L norm equal 1. So this is different with if you're given mu, this is an elliptic problem. So here we find the mu and the phi together, and this constraint. This is called time independent cross-disciplinary equation, or kind of nonlinear eigenvalue with a constraint. Okay. So of course you can see. So of course you can see here, if we know phi, the mu is called chemical potential equals this one, which is the energy plus something. So physical interpretation is so we have n particle due to interaction. N is the energy per particle, total energy divided by n. Well, mu is because the energy you need to add one particle or remove one particle. In some sense, the mu is the variation of the energy function to number of particles. In some sense, that way. Okay, so this is a setup. So here we want to find out the kind of minimization, ground state or some other states, not the bounded state. So and here we under consider this mu phi square equal 1. Of course, there are some other problems, like from laser propagation or other cases, they drop this one. Or given mu, or find a mu and given mu, find a phi. Okay, the different problem. Okay, here from this cold atoms, this guy is also there. Okay, so some question is we ask. So for this problem, you're given potential, harmonic or confined potential. For constant beta, lambda, and this is n, because n is a dipole orientation, additional freedom to play with. Okay, so basically you're given beta, lambda, and n. Question is there a minimizer? Is it unique? Some kind of mathematical question to ask, because we need to compute, right? You need to know what you want to compute. If the solution is unique, you know what you compute. Then, of course, you have a method, you let your measure set times go to 0, you convert that solution. If this is not unique, so which solution you want to compute? This before you do computation. Okay, there are some mathematical theory to show if my potential V is bounded below and confinement. That means V go to infinite when X go to far field. So this condition is such that this set S is compact, because this here are L to norm. So with this confinement, we show that my phi, if L to norm equal 1, it's go to 0 at far field with some rate. Okay, and so if my beta greater equal 0, which is the original contact direction, and my lambda less equal beta, greater equal minus beta over 2, and this condition, there exists a ground state phi g. And the ground state phi g is unique. Well, the post-contact ground state, if phi g is ground state, phi g can be written as absolute value of phi g times exponential I theta 0. Theta 0 is special independence. Okay, so the post-ground state is unique. For this problem, you're given potential V, confinement, as well as beta lambda in this region. The post-ground state is unique. Okay, and we can also show that with this rigidity, if beta less than 0, lambda case 1, no matter which lambda is his, or beta greater equal 0 and lambda bigger than beta, or lambda less than minus beta over 2. For example, if beta equals 0, if lambda equals 0, here's 3 dimension. If lambda equals 0, as long as beta less than 0, there are no ground state. Ground state means the minimizer. We can see that means we can find a sequence phi, say phi n. The E of phi n goes to minus infinite when n goes to infinite. So that means the limit of the set is 0. Okay, with this, so the proof is, I do not skip the key proof is, suppose you have a function phi here, with different you have this Poisson equation, right? And the key observation is dn, n is a unit vector, dn grad phi. This lets you grad phi, and this equals Laplacian phi, and equal rho L to norm, so equal phi L4 norm square. So this, you can say, all this included here, the coefficient is 1, not the arbitrary constant positive constant C. This constant 1. So that you give from this one, you can give this sharp condition here. Okay, and the other similar. So since you can say so this problem, this problem is a non-convex minimization problem. However, if I write it into a density rho, so if I define so-called E of square root of rho, this guy, as of E tilde of rho, this guy is so-called if I rho this one. So in terms of rho is convex. So in some sense, the minimization for phi is non-convex since the confinement is phi square equal 1. However, if we write it into rho, which is integration of rho equal 1, which is a linear function, so which is convex. So then you use convex theory. And for this non-existence, just choose this Gaussian. You play with epsilon 2, you can find the limit go to negative infinite. Okay, so then we can show that this is unique. Then of course how to compute. Because I said previously you do convolution. Convolution normally people do a Fourier transform. This is the only way, most efficient way to do it. And you see there's some logging phenomena. However, now if I write it into this PDE formulation, This is the operator formulation. So for this one, then we can truncate it to a bounded domain omega. Now, since as operator, we can truncate the bounded omega. We do not need to apply periodic boundary condition. We apply so-called dedicated boundary condition. With on boundary, we let phi on boundary of omega equal 0, not equal periodic. I'll show you later why this. Yeah. So we truncate boundary domain. What we do is you just do a gradient flow. So since you have a constraint, right? You just first ignore constraint using the simple method gradient flow. You can dt phi. This is a variation of energy. Then you evolve one step. Then you at the end of Tn plus 1, you do a projection. Then of course here the key here is you truncate the boundary domain omega. You apply the 0 boundary condition. Then if you do further computation, you do sine basis, not Fourier basis. Then you will see. So then for this one, you do backward Euler there, and then okay, in space you do sine spectral method due to this 0 boundary condition. If you do convolution, you can only do Fourier basis. You since you do Fourier basis, then you find you need the inverse 0 modes, and you will see that you can see from here. You can see this one. This is like a Poisson equation, right? Remember my phi square normally in Schrödinger in GP type. This guy integration over omega is 1 due to mass conservation. So this guy, if you do integration over omega, apply periodic boundary condition. So this guy, you have 0. This is where so basically something like this one. You have minus Laplace phi equals psi square on to omega. If you do periodic, so this is omega, right? This is equal 1. This one equal integration boundary of omega d phi dn. This equals 0. So let me say, of course, this cannot true, right? Let me say, if you due to this truncation, original whole space problem, there's no issue at all. But when you do truncated boundary domain, you do periodic boundary condition. You have this kind of. The reason is your psi square. Your psi normally will function, decay exponential fast. This guy, Poisson equation in 3D, only decay polynomial fast, like 1 over r, something like that. Okay, this just. Okay, let's show some result. So this plot here is given my potential is symmetric, sphere symmetric. Given my constant beta 207, computation lambda. So you can see this one, of course, my n is 001. So this guy is lambda equal minus beta over 2. This is the density, the contour plot of density, so isosurface plot. So you can see this is lambda equal minus over 2, lambda equal 0, lambda equal quarter of beta, half beta, 3/4 beta, and lambda equal beta. You can see when lambda equals 0, that is the isosurface plot is sphere. However, when lambda equal beta, you can see the ground state is aligned to the dipole orientation. Okay, so after, of course, you can do many other study here. You can do this simulation. So after the ground state, people want dynamics. Dynamics, of course, you're given the setup problem, given initial data. So this psi 0 could be a ground state of this problem and a different beta or lambda of v, or even n. So you can say we can in experiment you're given v, given beta lambda and n, your ground state. With this ground state you play with, you change beta, change lambda, or change n, or change v. So question is for this problem, whether this of course disperse PDE some theory. Okay, and again, one can just quick. So the problem is if the V is smooth and the solution locally exists, no problem. Again, if beta greater equal 0, lambda greater equal minus beta over 2, lambda equal beta is global existence. And also one can show that when beta less than 0, or this case, this similar as no ground, as there's no ground state. my V for this condition, like V is 0 or V is harmonic, this is always true. Then we can show that if psi 0, the initial energy has some condition, like initial energy is either less than 0 or some condition, there's going to phantom blow up from this model. Of course, experimentally, the test this blow up is mathematically game or is physics. They find that this, so this blow up, if this model from cold atoms of quantum physics, this blow up is artificial. This reason is original n-body problem, linear Schrödinger equation. Of course, mass conservation, anti-conservation, no blow up. When you from n-body to this one-body nonlinear problem, you only take a two-body electron interaction. Some other, the assumption is the density of the atom is not too small, and the wave function is not too big. In this assumption, you only take a two-body electron interaction into the mean field approximation. In reality, of course, when the density between two dipoles very small, due to if the interaction is attractive, or when the density become very high, some inelastic energy must be considered. So then people relatively add some experiment, physical experiment, take some damping term to take over. Okay, so this is theory. So of course, in computation, good. You just do using this kind of time sequence semester. You from time t to t plus 1. You first solve this free Schrödinger equation. You take it to, but remember here, due to this dipole term, you do when you do in space transition, you do sine basis, not free basis, to match the boundary condition. And for second time, you can see you solve this one. And here, good thing is you can see if you multiply second to both sides, you will find this dt absolute set square equals 0 for any fixed x. So this shows that at this, after this splitting at this step, the density pointer doesn't change. So this side, the only change is the phase. So due to this is conserved pointer-wise, so this Poisson equation, although this one only reduced to one equation. So phi xt equals phi xtn. So basically, you need to only solve a linear equation and a Poisson equation at Tn after the splitting. Has good property. Okay, again, you solve this one by method. So here, of course, I want to mention that due to this dipole interaction, which is a highly non-low, is a singular. How to the different ways to efficient and accurate evaluate it. So I have phi equal u dipole convolution. A simple way is you have a phi psi. You take a Fourier transform of this one, Fourier transform of this one, which is given here. You do the multiplication of the Fourier transform, then the inverse. This is called classical Fourier transform method. Do the convolution, right? Next one is my phi using this formulation. My position is this here. Again, if I know psi, I do sine transform for this equation. This is easy to do due to zero boundary condition. Then I do derivative of this one. You get this one. So this by you can do using this sine transform to do it. So of course this one is much extra than this one. The same computer cost. Again, this one still have some. The arrow can be improved from here, maybe 10 to the power minus 2 to single percent, like 10 to the power minus 6. Well, we later find a good method is called using the 9-unit for FFT. The idea is the following. So basically, we integrate or use the quadrature for some integration with singular integrand. You will lose accuracy. Okay, so you can see my phi equals this one. I write it into Fourier transform form. So phi of xt equal R3 u hat Fourier transform, right? Times rho hat. Rho is psi square times exponential I cos theta x dx. So basically write this one in Fourier transform, right? Now you can see in this one, classic way, if you do you're using this one Fourier transform here, and this is good function. This is good, but this one, due to, as I mentioned earlier, when psi go to 0 over this type, it's singular. So when you do using so-called in Fourier coefficients, Fourier space. If you use the Cartesian grid points, this one due to this integrand is singular. You have loose accuracy, so always cause problem. The key is behind is due to the truncation error here. However, for this one, for this integral R3, we're using spherical coordinate. You can see I just write this one into S2 cross R1. R1 is the epsilon of psi. So you can see if I do change this form integration by using spherical coordinate, the Jacobian matrix, this guy will comes in. So of course then you can say now you can say this guy u depth hat times this guy, this function is smooth function. So now if we using quantity to approach this one, because since the integrand is a smooth function, you will not lose accuracy. Of course, another difficulty is, normally in computation, my psi is in physical space, Cartesian grid points, like a square. Then you do take a Fourier transform, you get this rho square. This guy normally in computation is in Cartesian grids. Here we need this spherical type grids. So of course, how to interpolate from a Cartesian grids to this spherical grids? There's a very nice trick developed by Greengard and his group because from one grid to another grid can be very efficient by using like a Gaussian approximation and can preserve spectral accuracy. So basically, you can say when we do this simple trick here, we can basically the integrand becomes no smooth function. Then you do quadrature. So basically, let's remind us because there are some slogan in computer math community that same problem, the different formulation, they are equivalent in continuous level. However, when you design numerical scheme from them, their performance may be completely different. So if you choose a proper formulation, like you can say this formulation and this formulation, they are equivalent continuous level. However, if you ditch this one, you get a locking phenomena. If you ditch from this one, you get a good performance. So if you choose a good formulation, you will get maybe do a better job. Okay, in simple comparison, you can see we just take a row like a Gaussian. You can come to analytically. You can say if you do NUFFT, this is mesh size. This is the size of domain as a box. You can see that. You can say if my size is equal 8, that means minus 4 to 4 cube. You can say when h go to 0 smaller, they achieve the spectral accuracy very quickly. And basically, and also as long as the L not too small, they count for different h very quickly. However, if you do direct the convolution of FFT, you get even worse result. But even you do DST, you can say only when L very large, and you see our convergence. So this shows some kind of comparison. Here I show using this kind of new from the AUFT to approach the delta interaction. I show one result. But here this is a simulation for dynamics. What we do is at t equals 0, I fix my beta, lambda, potential V, and n. The depth order is n equal 0, 0, 1. I get a ground state, which is like this one. This depth orientation, the ground state like an ellipse. Then at t equals 0, I let my nt change from like chosen as sine t over 5, 0 cosine t over 5. I see dynamics. You will see the solution looks like the following. You can see it seems the density almost no change during dynamics. They follow the depth orientation. We try to use some kind of ansatz, like people do soliton or vortices to get some approach solution. So far, not to get a good result yet. Okay. Okay. So I show you precisely for dynamics, when the beta less than 0. Or when beta bigger than 0, my lambda bigger than beta or lambda less than minus beta over 2, the model should blow up. People say experiment also try to understand whether this blow up is physical or not. So this shows some kind of a collapse of BEC with dipole-dipole interaction. Yeah. So what they do is, again at t equals 0, fix my beta, my lambda, my potential, and my n equals 0, 0, 1. Have a ground state. Then at t equals 0, they change the lambda from say quarter beta to 2 beta. Okay. Then this, as I just plot here, is the absolute size square x 0 z t equals 0 is this one. This is concept. You will see some kind of experiment. The opposite is called Clover phenomena. You can see due to this, when beta lambda large, due to strong attractive interaction, they go to center. Then they form some kind of Clover phenomena in the simulation. Okay. So this shows the method really works well, can capture. Of course, in this per simulation, this collapse, we need to add quantic damping to arrest the blow. Otherwise, the model method tell you they blow up at final time. We add quantic damping. Normally, no blow up. In fact, still a mathematical question is, you get a quantic damping as long as the damping is a constant bigger than 0. No blow up. Simulation shows no blow up. But whether can one prove no blow up? Still open. Okay. I have a few minutes. I just talk about the debris reduction. So, in many experiments, the trapping potential V harmonic. However, this gamma x, gamma z, the 3 constant could be different scaling. The one case is gamma z much bigger than gamma x, gamma y, like a disk shape. The other, of course, here you have n is n1, n2, n3. So this n dipole orientation introduce one more freedom. Okay, basically this is the unit vector. So this case is like if no lambda, of course the reduction is very simple. Now with this dipole orientation, the other case is my from 3D to 1D or cigar shape. My gamma z much bigger than gamma x, and gamma y also much bigger than gamma x. Okay. So of course, when lambda equals 0, there are a lot of exist study, even like formal asymptotics, numerical results, or even rigorous proof, all down there. Of course, I want to mention here from n body to this mean field for lambda equals 0. That is Lieb, very famous work by formal work by Lieb, Seringe, and Johansson, and also by this L. Dot and Yao, Shiley and Yao. They have like over 100 pages paper to show how to this reduction. But here what we do is from 3D to 1D. If suppose the trapping potential is anisotropic. Obviously for dipole 1, before us, this some people using the convolution formulation. What we do is using this formulation to do it much simpler. Okay, so the setup is the following. I suppose my gamma x, gamma y equal order 1, and the gamma z is much bigger than 1. So I suppose consider when gamma z go to infinite, what happens? For mathematicians, something go to infinite is not good. We like to something go to 0. So we choose epsilon equal 1 over square root gamma z. Then you can say gamma z go to infinite, corresponding to my epsilon go to 0. So now my potential v can be written as v 2 dxy, anything, plus z square over 2 epsilon power 4. So this is the leading term. Then you can say the linear operator minus Laplacian plus v can be split into minus 1/2 Laplacian probe xy direction plus v2d plus lz. Lz is minus 1 over 2 dzz plus z square over 2 epsilon power 4. So basically, this case is in z direction is strongly confined. So this one, if you change a variable like z tilde equal epsilon z, so this guy can written as 1 over epsilon square. This guy. This is the classical standard harmonic oscillator Hamiltonian. So we know the eigenvalue of this one is order 1. So it means the eigenvalue of this LZ, or the energy, is roughly at 1 over epsilon square scaling. And this guy, the energy is order 1. So you can see from this kind of decouple, you can see in xy direction, the linear term is order 1, and this one is order 1 epsilon square. So if you do some perturbation, the perturbation will be only in this direction. This one almost no effect. So with this decomposition, we can assume the following ansatz psi. So psi xyzt can be written as exponential minus it over 2 epsilon square psi xyt plus times omega epsilon z, which, well, omega epsilon z is written in this form. This one is the ground state of this one. And you can say, for this omega epsilon z, when epsilon equals to 0, this will convert to a Dirac function. Yeah, this one. Okay, now if I plug this ansatz into my GPE in 3 dimension, you do some massage, you get the equation in 2 dimensions, which is like this following. I dt psi, so this one. This is the final one, because here you get a beta minus this one, and times this term here. This n perp is n1, n2. And this little phi is written as u epsilon 2d convolve psi square. Well, u epsilon 2d is this one. This is for n epsilon small. You get like a quasi 2D model. And interesting here, you can see if I let my epsilon go to 0 from this kernel, the limit exists. And this limit can be given here. Limit go to 0. Basically, you can see, okay, let me go back here. Okay, if this one, you can see if I let my epsilon go to 0, this go to 0. Okay, this R, no, here S, so this can be integrable. So basically, when you let epsilon go to 0, the U epsilon 2D xy will go to some constant times 1 over R. This R is this one. So basically, this phi will epsilon go to 0. This one will go to phi xy t equal 1 over some constant c times 1 over r convolve set square. So basically, again, this is understandable. You can say in my 3 dimension with a Coulomb interaction for the Poisson equation, which is 1 over 4 pi r. Of course, in 2 dimension, right? You confine the 2 dimension, the particle interaction is still Coulomb. So which is still, the kernel is 1 over r. But this r is in 2 dimension, not 3 dimension. And in 2 dimension, 1 over r is no longer Coulomb interaction. It's no longer the Poisson operator. Poisson operator, the quantum solution is log r. So this shows that this 1 over 4 pi r, some constant 1 over r in 2D is corresponding to minus Laplacian perp to power 1/2 this one. So you can see this fractional or square Poisson operator, square root of Poisson operator in 2 dimension, corresponding to Coulomb interaction in 2 dimension. That means you can confine this dipole from 3D to 2D. Basically, z direction is not uniform. It's a Dirac function in z direction. Basically, my omega epsilon z go to Dirac z. Yeah. So that's my approximation in 3D. The integration epsilon square is still 1. Okay. So with this one, you can study this model in 2 dimension. It's like exist, ground state, whatever, a script. Okay, we have some theory to show that the weapons of the 2D reduced model and also phantom may happen. And we can show that when lambda beta small order epsilon, which is 1 over square root of gamma z, this is my solution to 3D problem. This is the solution of this is my solution of the reduced model. This is the highly oscillator in time, and this omega LZ. This the position is converged linearly with my epsilon parameter epsilon z. Then omega epsilon, which means when gamma z go to infinite, my reduction converge in terms of 1 over gamma z at a rate of minus 1/2. some Z. Okay, I skip this one. Okay, similar interest to can do also to from 3D to 1D. Again, we assume is here just change a little. So just suppose gamma x equal gamma y, and much bigger than gamma z. Gamma z is order 1. So then we consider when gamma x goes to infinite, what happens? So then we assume this v exponential equal v1 dz could be anything plus x squared plus y squared over 2 epsilon to power 4. And epsilon is 1 over gamma x squared, because the original is 1 over gamma x squared times x squared. So with this one. Again, my linear operator can decompose to minus 1/2 dzz plus v1d of z lxy. So this one is here, which is, again, which energy is 1 over epsilon squared. So again, you can see this part, the energy is order 1. This part of the energy is order 1 over epsilon squared. When epsilon small, you have a clear scale separation in energy level. So again, with this kind of understanding, the proper ansatz should be this one. So here is exponential minus it over epsilon squared psi zt omega epsilon xy. So this one is basically the ground state of this one. Again, this when epsilon goes to 0, this guy goes to Dirac xy in R2. So then you plug in, you do calculation, you end up with the following 1D model. Again, here this phi equal u epsilon 1D convolute this one. And the interest here is u epsilon 1D, this guy. You cannot let epsilon go to 0. This one, when epsilon goes to 0, there's no limit. And number 1. So that means we can confine this dipole from 3D to 2D completely when epsilon goes to 0. When gamma z go to infinite. However, you cannot confine this dipole from 3D to 1D completely. There are no 1D. Basically, I say something that 1 over epsilon x in 1D is not a kernel. In 2D it is, 3D it is. Okay? And the other thing you can see, observe is, you can see if from this reduced model, when epsilon, so this of course when epsilon like bigger than 0, much less than 1, this can be a approximate model in 1D. And there's a magic angle. You can see if my original problem, my beta taken as 0, my lambda is non-zero. So if my original 3D problem, if beta equals 0, my lambda is non-zero. The original 3D problem is a nonlinear problem due to this dipole. However, you can see if in this case, you can see if I choose 3n3 square equal 1, so there's a magic angle, because here you can see the trapping potential is, so in xy direction is strongly confined. Z direction is order 1. And if the angle 3n3 square equal 1, you can see this term go to 0, this go to this 0, this term go to 0. In some sense, when in my 3, if beta equals 0, lambda is non-zero. If in the cigar shape confinement, there's a magic angle, basically the 3D problem. They perform like a linear problem in 1 dimension. Basically, you can say this go to 0. Also, lambda is 9, but this guy go to 0. Beta is 0. So interesting here. Of course, three linear problem, right? Like a superposition, all kinds can happen, but a non-linear is not. Okay, I can skip this one. Yeah, okay. Of course, for this dipole 1, if you add rotation term, so you can see you have dipole, their orientation, their trapping could be different orientation, different trapping, like a cigar shape or disc shape. The dipole, there's this orientation, and the orientation n could be 001 or 100. And then if you add this angular rotation, so since here my LZ is z direction angular moment rotation, then you have one more term. So of course the energy is this one similar, then the vortices will be changed. So for example, if you consider my n choose as sin theta 0 cos theta, if theta, you can say theta equals 0 is 001. Basically, is the dipole direction is a part of z direction. But however, if I choose my theta equal pi over 2, so n become 1, 0, 0, 0. Okay? So you can see here, if I even choose my trap is radial symmetric. sphere symmetric. You can say this is a ground state. Okay, so let me see. Yeah, this density. So I fix my interest is, okay, you can see if my n, let's say my theta from 0 to pi over 2 due to my, okay, because then you can see this is my ground state, but when I take it, first row is for omega equals 0, no rotation. You can see when n from 001, which is radial symmetric, to this to a circle contour plot to a ellipse. This is like a first vortex state. What is state with one number 1? You can see here when n is 001, I get this like the density like the we'll find like a f of r expression I theta, which r is a polar radial coordinate. It becomes this one. This one is no longer like a radial density, no longer radial symmetric due to this anisotropy. Again, then if you took this omega large, you can see when theta equals 0, which is like the lattice is abrasive lattice in the center part, middle part. Every 3 vertices form a right triangle. However, if my theta become large, or even pi over 2, the lattice become parallel. Okay, we even do some kind of systematic study. You can see here this is for different theta. We see here from 0 to pi over 2, and this one, this axis is for different epsilon dd, which epsilon dd equal my lambda over beta. You can see this one when lambda equals 0. Okay, somehow when theta is 0, which is abrasive lattice, become like some kind of change, and especially when dipole direction become large, which is like this corner, this part, which become parallel lattice in simulation, while in the lattice. So again here with this dipole orientation, which due to the dipole orientation, which adds one more freedom, like one more freedom to play with. We have a lot of structure. Okay, with this dipole with lattice, we a few years ago with joined with the Dieter Jaksch and the group, we want to study so-called impurity. So basically, what is lattice, which look locally like with so-called optical lattice potential. So we study the GP equation coupled with so-called impurity, like one of your external particles. So the impurity could be, so you can say, could be one impurity, like ion, into the ground state, like fall in. So the what is called the lattice, the quantum lattice call, or two could be fall together due to the impurity interaction with the mean field with the condensate. There could be one there or two there, with which we build this called Haber-Bandel model to explain the atomic impurity. Okay, I think I can skip this one. Of course, my time is over. I can skip this one. So just brief conclusion is, well, with this dipole interaction, which is anisotropic, non-local, they introduce a lot of interesting mathematics there, and a lot of experiments. From what I heard, especially can say due to this, the dipole part is repulsive, part is attractive. So they can form a lot of studies there. Again, so the new problem there, when you new model, some material challenging also in computation. When computation, again, some technical messages, especially for students, is when you have a problem, there's a model, the model could have different equivalent formulation in continuous level. When you design numerical scheme, you need to choose a proper form, which the different formulation you could end up completely different than numerical methods, and some may perform better. Okay, I think I stop here. Thank you.